try to ask through this kind of online text. Okay, so now first I want to give you some outline about today's lectures. First is about what is microsystem technology, and then talk about why it's so popular. Well, at this moment, I think one of the important application of this MEMS will be what? In your smartphone, right? Your smartphone has at least 10 sensors that become very important. And of course, this every year, people make at least 100 million or 200 million of this kind of MEMS microphone for smartphone. So this become microphone and many sensors for smartphone. So it's a very big business now, at least $1 billion business. Okay, and then talk about the history of this particular field study, and then talk about current and future application of MEMS, and then we'll talk about some representative MEMS device, including the micro pressure sensors, accelerometer, MEMS micromirror array, inkjet, pinhead. I believe all of this kind of MEMS device is very common now. Okay, and then talk about some basic idea about microfabrication, microscience, and summary and conclusion. First is we talk about what is your name. So in comparison with the previous lectures about the conventional mechanical engineering, so this MEMS has many names, right? For example, we have a microsystem technology, or MST. It's more popular in Europe. And then we also have a MEMS. Okay, it's a short name for micro electromechanical system. It was used in United States. And then we also have a microengineering, sometimes used in UK. And then we have a micro machine written in this kana in Japan. I would say MEMS sensor, I think is Japan is one of leader in the world to make a very type of a MEMS sensor. Okay, and then micro machine in Chinese. Okay, so at this moment, more or less, all these terms, MST, MEMS, microengineering, micro machine, they are more or less referred to same topic we'll talk about today's lectures. Okay, and then next we'll talk about how we define this kind of a MEMS as a field study. Right? Basically, MEMS is the study of making machine in micro scale with fabrication technique used in IC industry or semiconductor industry. And the size range from micrometer to millimeter. Micrometer means 10 to power -6, and millimeter means 10 to power -3 meter. Okay, and here MEMS actually are the system that integrate sensing, actuation, computation, control, communication, and power. So it's a system engineering subject. Well, in compare with many other topics you learned in previous lectures, so it's very different, I would say. Okay, and of course, it requires you have a much more understanding on ME, mechanical engineering, and also EE, microelectronics, semiconductor engineering. So you are able to work on this MEMS engineering. So let's look at the size effect, right? So when we look at this size effect from macro scale, gradually we shift into smaller micro scale, right? So this is typical size for traditional engineering, from 10 to the -3, 1 millimeter to about 1,000 meter. Okay, if we scale down to the smaller and smaller, let's look at what happened. It's smaller and smaller and smaller. What do you think? So our MEMS actually, the size range between the boundary between 1 millimeter and to about 1 micron, okay, or 10 to the power -6, okay. So of course, if it goes smaller and smaller, so let's give you some, ask you some basic question, right, in terms of size. So I don't know if some of you know about the size of your hair. Do you have any idea What's typical size, diameter of your hair diameter? Huh? This is something quite common, right? Everybody, unless you are very old, so most guys still hair. So what's typical size of the hair? Huh? What is the typical size? Typical size of human hair? Do you have any idea? Huh? Your hair, right? What's typical size in terms of diameter? Okay, so we have student, it's about 0.1 millimeter, 100 micron. This is typical diameter. So our men's actually is in this range, about 100 micron or 10 to the power of -5, the typical size. So our micro machine is really the size of hair. So that we want to make a micro machine in this range, okay? And so that here, if you try to look smaller and smaller, of course, we have another kind of field study we call the nanotechnology. So the size typically is less than 1 millimeter to about 1 nanometer. 1 nanometer means 10 to the power of -3. At least from my own research field, I'm working on MEMS and microwave for about more than 20 years. So that we think, at least in my lab, we think it's more practical to do some nano research on nano device, nanostructure on micro machine, and it will be more practical, make a practical MEMS product and devices. This is for my own research experience, okay? And so there's another special field we call biomedical area. The size range from 1 nanometer. Typical like a DNA size, it's about nanometer. You know, the double-strand DNA is about 3.4 angstrom, about nanometer. Okay, and then we have cell. What type of cell in human body? Cell. Huh? Any idea? Red blood cell. It's around 6 micron. Okay, it's this size. Less than this kind of 100 micron. So this is typical size. And then, so that this is for biomedical area, we are study from this DNA, cell, tissue, and human size. Okay. So again, now talk about the history of MEMS. Actually, we can talk about this from the 1947 invention of transistor. Right, so that the transistor is one of important device product people in human history try to make. Right, now we making billion or trillion of transistor. Right, your smartphone, the new smartphone, we have a billion of transistor. Okay, so that now how we can use this kind of semiconductor process to make the MEMS sensor. Right, so this has become very important thing. Okay, so that right after invention of transistor in 1958, people already think about silicon-based strain gauge. Okay, strain gauge basically is a somehow sensor, or MEMS sensor to what? To measure the strain. Strain actually is deformation of mechanical structure and normalize, right? The deformation with their original size. Okay, so that of course at the same time we also see that we have a first IC invented by Jack Kilby in TI, Test Instrument. Of course, later on, I think Jack Kilby got Nobel Prize because this invention becomes so important and ubiquitous. Right? Nowadays, you have IC is everywhere. Right? Your smartphone, your computer, your iPad, your like wearable device. With every thing you're seeing your daily life, you have so many IC. Okay, and then in 1960, people also come with the first silicon pressure sensor demonstrate. Okay, by this Cool Light company in the United States. Of course, nowadays most of new smartphone actually also have pressure sensor. Okay, and then in 1967, people also invent this kind of surface micro machining, right? And make a transistor, resonant gate transistor. Transistor is a 3-terminal micro device, and it is for electronics. And then resonant gate, that means some device is some vibration. No, and then so that in 1970, people already come with silicon accelerometer, also developed by Colite company. So again, now your smartphone has this kind of very advanced 3-axis silicon accelerometer. And in 1977, people also think about capacitive type sensor, and also the 1979 SP also come with first thermal inkjet. So thermal inkjet is also one of man's device. Okay, so in 1980, Kurt Peterson is one of a pioneer in this kind of men's industry. He has started a series of men's company in the United States, and when he was doing research in IBM research, he has one very important review paper about silicon as men's micro machine material. So he also comes with this kind of silicon torsional micro mirror. Okay? And then later on, we also find a series of research done by UC Berkeley, United States in California. So that Professor Hall and Richard Muller, they come with a series of polysilicon. Polysilicon is one of very important material in IC and semiconductor manufacturing process. They try to use polysilicon to make micro machine devices. And then later on, there's a series of this kind of men's research in United States and many other places in Japan, Europe. And then in 1990, also Bilco is company in Europe also make a microfluidic device SPR for bio application. And then in early 1990, and one important thing, US DOD, they have a DARPA office, try to provide the big money for research in this area for the men. Remember, and DARPA actually have provide funding in 1960 for what? For internet. That time they called ARPANET. ARPANET, the first internet connection is from the UCLA to Stanford. Okay, so of course now internet becomes so important now. So you have a smartphone connect internet, you have a IoT application and see. Okay, and then of course in 1993, Analog Devices also make the first surface micro machine accelerometer was sold. The first one ATX50, and then 1996 we have a digital micro mirror array commercialized by the TI. At that time they called DMD. Later on they called digital light processing. In year 2000, so people also try to think about optical micro machine, optical MEMS for what? For internet communication system for internet. And another important milestone is 2007. Steve Jobs in Apple, they try to use this kind of MEMS accelerometer for iPhone. And of course, Apple, they don't call this kind of micro accelerometer. They call the G sensor. Actually, it's an accelerometer for what? For tilt sensing. How the iPhone try to use this kind of MEMS accelerometer? So basically, this kind of accelerometer has a very important application for what? For human-computer interface, right? So that if you have this kind of web browser, right, and then you try to tilt, you tilt your smartphone app, and then in this case, then they would automatically rotate this orientation of this kind of interface, right? So this is the way people try to use, right, for smartphones, so that this is increase the human computer interface, right? So that is the first application. Let me show here. That means you tilt seeing, and then smartphone browser will change its orientation, right? So that is some special application in 2007. Of course, later on, once you more and more MEMS sensor, motion sensor, and then you can use for many other applications. Okay. So again, here I show you the one important milestone. Okay, so the invention of first transistor by this, I think the researcher in Bell Lab in the United States, okay, in 1948. So that, again, this is an important milestone for human history. So that we try to what? How to turn sand into silicon wafer and do micro machining to make transistor and then make IC, right? So that it's very important milestone. And then of course nowadays in the past many years, people really make more and more transistor in IC. So that you see more than 10 years ago we have about 100 million of transistor using make 19 nanometer technology, and then nowadays we have 2017. Apple have using 10 nanometer transistor and make this processor in your iPhone is about 4 billion transistor. And then last year, Apple have a iPhone, I believe it's iPhone 10, so that we're using 7 nanometer transistor with 7 billion transistor in your smartphone, right? So made by TSMC. And then, of course, not only Apple, but Huawei and Intel, they are all going to nano transistor and make billions of transistor on IC. Okay, this is a quite important thing, right? So that I don't know if you have any idea about the cost, how much you cost to make this kind of advanced 7 nanometer transistor CMOS fab. Any idea how much TSMC invest to make 7 nanometer fab for fabrication of the IC for your smartphone? Huh? How much does it TSMC spend? Huh? TSMC spend to build the 7 nanometer CMOS fab in Taiwan? Do you have any idea? Any idea? Well, one student say about $10 billion. It's close, actually. In reality, if you look at the public report, TSMC spent 18 billion US dollar, 18 billion, okay, US dollar for 7 nanometer fab. Okay, I mean 3 billion for R&D and 15 billion for to build the fab. To build the fab, okay, this nano fab, okay. So it's a huge money, huh? 18 billion. Think about one company can afford 18 billion to build a fab. That is really amazing. At this moment, about 1 or 2 years ago, only 3 companies in the world can afford this big money: Intel, TSMC, and Taiwan. Do you understand? So it's very, very expensive. Okay, so it's not only is cost a lot of money, but also what you also need to have a technology. If your money, you have no technology, you cannot really make this kind of advanced manufacturing process. Okay, do you have any idea how much TSMC will spend for 5 nanometer CMOS fab in Taiwan? Huh? How much? How much for 7 nanometer fab? Huh? For sure, it's bigger, even larger than 18 billion. Well, according to public, it's about 25 billion. So that's why at this moment, only 2 companies in the world continue to go beyond 7 nanometer, TSMC and Samsung. Okay, so it's it's really so expensive. Okay, anyway, so this is a very, very special thing, right? So that of course in China, so China import 200 billion US dollar of IC, right? So that how China can really make this kind of IC semiconductor or a chip, also main sensor, to make a product. It becomes an important issue. Okay, so that so this is, but it's still not easy, I told you. Okay. Anyway, so here I told you about the important thing. The next one talk about is Moore's law. Right? So all of you have heard about Moore's law. Right? So that again, this Golden Moore, there's this kind of idea in 1970, right? When Intel tried to make the like early CPU. They use about 1,000 or 7,000 of a transistor to make their CPU in 1970. Then he has a vision to think about the future, so that you see CPU power will double every 18 months, and number of transistors will increase dramatically, exponentially, right? Nowadays you can see, as I told you, your iPhone 10 about almost 7 billion transistors. So this is something quite amazing. How about MEMS? So can we leverage the kind of semiconductor industry to make this kind of billion of sensor? So that is very important thing. And here I show you the roadmap. ITIS is international roadmap for semiconductor industry. So that this is announced about 9 years ago. So that of course in the industry, people continue to make smaller and smaller transistor. At this moment, 7 nanometer is the mainstream. Okay, and for me, I also try to use TSMC to design the CMOS MEMS sensor. My lab using 0.18, 100 nanometer process, CMOS process to design a CMOS MEMS sensor. You see, so that so if you go in small, okay, so it's very expensive. And for 28 nanometer, okay, CMOS process, if you want to design to make this kind of IC chip, it's very expensive. So that our colleague in EC department try to design this kind of 28 nanometer CMOS process. Do you have any idea how much it costs? Huh? Actually, if you send your design to TSMC to make a 28 nanometer CMOS process, right? And then so that one tap out is $500,000. $500,000 Hong Kong dollar is 500. It's about 0.5 million Hong Kong dollar to send your design to make the chip. So that not only try to make it CMOS fab, nano is expensive. How to, once you have design of advanced IC, you send your design to TSMC, common fund to make is also expensive. Okay. Anyway, so now at this moment, I think industry almost not going to so small, right? 6 nanometer, 7 nanometer, 5 nanometer, you almost hit the wall. The people say most of almost reach the aim. So that how we continue to work on this kind of let the industry to grow, so that people think about more and more. That our semiconductor process not only make a more and more transistor, but also can make more and more different devices. It's analog IC, you have wireless communication IC, your PAS device, high power sensor, main sensor, actuator, and biochip. So these are the future. So people will continue to not only make smaller and smaller, but also make more and more different kind of device using similar process. So that at this moment we have, from my point of view, we have the big business will be IoT, Internet of Things. So that the IoT, the sensor with the AI, and also the VR, AR, and MR. So I think you probably have downloaded some smartphone app for virtual reality AR application, right? So that the MR. So all this kind of VR, AR, MR need the main sensor to what? To check the human body motion, and then try to display with kind of like a display, and then do something, right? So that this has become a very important thing now, and the people believe will be very big business in the short term and long term. Okay, so that of course there's another thing, people cannot go beyond to 5 nanometer. Think about what's the future. Well, not only make small and small, and then we think about how we go 3D, right? We reach the limit of the max nano transistor, and then how we grow and make this kind of a multiple layer of the 3D IC for this kind of integration. SIP, system in packaging, for iPhone 10's processor. TSMC are making this kind, not only the CPU, but also memory chip, and also passive device, and then all integrate in microfabrication process. So that is the future. So this SIP, system in packaging, become very important, okay? Because SoC is important for this electronics, right? But if you want to integrate wireless communication with other kind of device sensors, so that sometimes it's very difficult to integrate in one wafer. So that in this case, we try to do some 3D integration. That is the future. Okay. Then next one talk about is the state-of-the-art MEMS chip, so that we have an analog device, this kind of MEMS accelerometer. So this is the ADXL202. So a 2-axis MEMS accelerometer. Actually, in your smartphone, actually you do have this kind of 3-axis accelerometer. To, well, of course, you can download the app, free app, and then try to turn your smartphone into the this kind of sensor to measure the acceleration. So that at the end of this lecture, I give you this kind of online. You can download the free app, so that try to look at this kind of how the output sensor output from your smartphone, the sensor, not only the accelerometer, but also the gyroscope, micro gyroscope, and the magnetic sensor. Okay, and of course we also test TI's DOP. Is typically now we have about 1 million by 1 million of micro mirror integrate on this kind of microchip. Think about why in like a typical Boeing airplane. Do you know how many components we have in airplane? Typical thing we think about, we have at least more than 1 million components for airplane. But now we can reshape using micro machining. We can really make 1 million of micro mirror, and integrate with microelectronic on this small chip. So this is something quite important. You think about how we can make more and more different type of micro machines. Okay, and of course, micro machine sensor is important, but also we can also think about other things. So this is show you about a series of micro gear driven by micro engine. So again, this is a unique application proposed by U.S. National Lab, and the idea is not more for smartphones. Think about how we can increase the security of this kind of nuclear weapon, right? You see, we have many computer electronic systems. If you connect internet, really have security issue, right? So the idea in this lab is think about how use micro machine to increase the security, right? For this kind of thing, right? This is a pure micro machine thing, right? So that avoid the kind of hacker thing, right? That's quite experience application. Also, MEMS market continue to increase exponentially. Okay, so this is all market research result, but you see now, I think this, I will show you more data in the following slide. So this continue to increase in the billion-dollar business. Okay, so especially for IoT application, ALT is becoming insane, right? So again, MEMS market in the beginning, again, we have a accelerometer for the automotive industry airbag, and then with a MEMS microphone for smartphone, and also we have additional RF MEMS for your filter, right? Your smartphone has a very advanced wireless communication system, so that you need this kind of RF MEMS device, RF MEMS filters, and also you have a gyroscope, and healthcare monitor for this kind of new type of smartphone or wearable device. You can also look at the human body tracking, and also for those smart watches, and also detect your heart rate, right? Like here, I show you we have this kind of smart watches or wearable sensor, right, to detect your this kind of vital sign for the human healthcare, right? So that is become quite important thing in the near future. Okay, and of course, RF MEMS is an important area now, not only for smartphone RF MEMS device, also for 5G communication system. So that people think in the near future, the market size continue to increase dramatically. So that's something quite important. Unfortunately, to able to design our MEMS require a very good background in mechanical engineering and the microelectronics and things. So it's very difficult. Now, you want to now be a good engineer in this field, you have to master both in ME and E. Okay, that's something quite important. And of course, MEMS has more and more applications. Right? Accelerometer, gyroscope, it becomes so common in automobile industry, for smartphone, for your this kind of smart watches, and also for what's this? This is Amazon Alexa. In China, we also have a Xiaomi Yinxiang or some of the thing, right? So basically, what's this? This has an array of MEMS microphone and with wireless communication. And once you talk to this kind of loudspeaker, and then the voice will connect to the cloud, right? Server with AI and recognize your voice, right? And do many work, right? So this become very, very important now. Beyond smartphone, we have this kind of smart IoT device with AI. So that is the future. And of course, here I show you about this market research report done by Nikkei Micro Device. It's a good way to show you about this kind of the market now in the past many decades, right? So people in industry think from 1970, we have very strong demand on IC similar industry actually grow very big market. So why is the revenue in US dollar billion dollar? You see, from 1 billion, 10 billion, 100 billion business, and then so that gradually this ICs become so common for everybody life. Not only computer, your watches, your smartphone, your iPad, tablet PC, and the wearable device, and all this need this kind of IC. And then in 1990, we have display, the second big business, right? All the portable electronic, we have display, right? Display, and this is it's like your face, right? And then third way, actually start from about 2005. So this main device, including ears, your eye is a sensor, right? That means what is eye in your smartphone? Well, your eye is for smartphone is this kind of small image sensor, right? Nowadays, most likely your smartphone has at least 2 small image sensor, front and back. Of course, advanced smartphone has 2 or 3 this kind of small image sensor becomes so important thing, right? And then you have an array of MEMS microphone in smartphone, and also this kind of smart loudspeaker, Amazon Alexa. Okay, all this need this kind of sensor. Okay, and at this moment, our current application of this MEMS, including again pressure sensor and all day for engine in a car, and then disposable blood pressure sensor in hospital, and then accelerometer for airbag system in the car, and then what? All the video game. I believe many of you like to play the video game. You have a Wii, Nintendo, Xbox. All this need this kind of MEMS motion sensor. Okay, of portable electronics. You have a smartphone. You have a tablet PC, iPad, all the things. So all this also have a MEMS motion sensor. Inkjet also has MEMS product, and digital micro mirror, DOP for computer projector and TV, and portable, the kind of biosensor and DNA sequencing thing, right? At this moment, actually, you find people really make this kind of portable size of DNA sequencing machine using the micro and nano fabrication process stuff. Yeah, so that is the kind of real product now. For example, this kind of Oxford nanopore in UK, they really make this kind of a portable DNA sequencing chip. It's an Oxford nanopore, so that it's not a dream, it's a real product now. Because Oxford, let me show you this thing. It's a Oxford nanopore. Okay, they make this kind of smartphone size the DNA sequencing machine. It's a real product, okay? Yeah. And then, of course, we also find many applications for inverter guidance and control, microgyroscope, and MEMS IMU. MEMS IMU is a combination of a MEMS accelerometer and also MEMS microgyroscope and also additional sensor fusion program. And so of course we have a micro magnetic sensor. Magnetic heads also quite important for computer hard drive, optical MEMS devices, and bio MEMS on chip, right? So that in the near future, when say this kind of a microfluid with a micro biosensor is important for food safety and environmental monitoring, right? So that especially in China, we have a lot of problem, air pollution, water pollution, and food safety. So that how we can come with this kind of low cost, high performance biosensor to enhance the safety, I think is will be quite important in the near future. Of course, we also have this kind of communication component. As I told you, every smartphone has at least 20 to 30 of this RF MEMS filter, because FBAR filter. So that become quite important thing. And only 2 or 3 companies in the world try to make this kind of FBAR filter for smartphone. So it's a very big business, FBAR filter, okay, for smartphone. So this is the RF MEMS device. Okay, every smartphone has at least 20, 30 this kind of filter. So the insane, if we have 100 million of smartphone, so that means you have 100 million multiplied by 10 or 20, so that it's really 200 million or 300 million of this kind of RF MEMS device. Now you need to make, right? So there's a $1 billion business for sure. Okay, but only about 2 or 3 companies, not like one company in like United States, actually. And then also we have okay, anyway, so that here we also have an additional device about this kind of power MEMS. At this moment, you see your smartphone has a big problem, right? Your processor is very powerful, but your battery can only last for 1 day, right? So that can we make it kind of new type power MEMS device? So yeah, in the future, smartphone, you can charge your smartphone battery and you can run smartphone for 1 month. I believe all of you want to have this kind of smartphone, and so that the power MEMS will be also important for this kind of mobile phone or IoT sensor. And military MEMS, how we come with micro NBC detector, detect the nuclear, bacterial, chemical warfare. For example, several years ago, we have Japan have this kind of a nuclear power plant of this kind of damage, and how can we this kind of low cost IoT sensor, right, for monitoring about nuclear power plant safety and bacteria. Why do you say? So that in the building, we have air conditioning system, right? Commercial air conditioning, we have chilled water supply. How we can have this kind of low cost sensor detect monitoring of bacteria, no, monitoring for air conditioning system. And these all are become very important. Okay. And then, of course, traditionally, we also have the MEMS for the automotive industry, right? So that we have a MEMS pressure sensor for engine. Why we need this sensor for engine? Basically, we control this kind of the intake of air with fuel, control the mixing of air and fuel for engine operation, right? It's an important thing, and we have a MEMS accelerometer to replace the mechanical switch for airbag system, and we have microgyroscope for stability control, and then so these are traditional application of MEMS. Of course, in the near future, we'll a lot more sensor for the car. Not only this kind of sensor, which I mentioned in previous slide, we have oxygen sensor to monitor about oxygen intake, control this kind of improve the efficiency engine efficiency for the engine, and also of a man's airflow sensor, and we have a temperature sensor to monitor the condition of the car, and the pressure sensor for tire TPMS system. So basically, in the future of smart car or self-driving car, actually we're going to have even more sensor like a LiDAR, man-based LiDAR, right? You know that Google have this self-driving car. On top of this car, have this kind of mechanical rotating, this kind of LiDAR, right? So, but this is so expensive. How use man technology to make this kind of advanced man's LiDAR for self-driving car? This is a very important thing, huh? Man's LiDAR for self-driving car. This is a very important business, but it still take time to develop reliable this kind of man's LiDAR for self-driving car, and also how to have additional sensor, right? Like advanced thermal image sensor, infrared sensor, or this kind of millimeter wave sensor, or ultrasound sensor for smart car. I think this is also very important. And then, of course, MEMS have been used now for airbag, optical switch, inkjet, also DNA analysis, also used for this kind of camera. Right? We install this kind of MEMS motion sensor for stability to minimize vibration, because when you take a video for smartphone or camera, so this kind of camera, your hand shaking. So how you use additional this kind of sensor to OIS stabilize this kind of smartphone or camera. So this is an important thing, right? Of course, for some new smartphone like iPhone 6 Plus, actually there's actuator like to vibration control, so that you can take a much better video without the kind of shaking. Okay, so all this become so important now. Okay, and of course we also have a TPMS to measure the pressure of the tire. And I remember 7 years ago, U.S. government required all the new car to be sold in U.S. They have to have this kind of TPMS to increase the safety of car, and also TI have DLP for computer projector, and then you have a video this kind of Wii, and also you have iPhone smart device. All this need the sensor, and of course in the near future we have a lot more. For example, main sensor for this kind of antenna, and also the IF-man switches, and additional IF-man other things. So this become very important thing. And here I show you, this is the summary from Qualcomm. Qualcomm is number one maker of this smartphone, the processor, right? So they have basically this is a roadmap. At this moment, your smartphone has a accelerometer, magnetic sensor or magnetometer, micro gyro, ambient light sensor, proximity sensor, pressure sensor, touch sensor. Right? Your smartphone, when you use finger touch, actually there's additional sensor that can sense your touch sensor, and also have a fingerprint sensor, microphone, and other thing, right? So that the haptic feedback. I think new iPhone, they have additional small vibration motor. So you touch this kind of smartphone screen, and then provide this kind of vibration and haptic feedback. So all this become very common. Of course, some new type of a smartphone will have more and more sensor for sure. Also smart watches, right? Some smart watches or wearable sensor have additional that measure the heart rate sensing and other things. So that of course, once you have multiple sensor, of course, there's additional software. People can try to look at your health care. For example, for iPhone, you have a health app. They can try to look at what once you can measure the motion, and then look at your human activity, right? Like for example, walking, running distance, and step and fly and anything, right? So this become very common and important for to monitor human body and conditioning and health care. Okay. And then of course in the near future, right? So this is show you about the the milestone, right? So in 1990, MEMS have been used in automotive industry, and then since year 2000, we have a consumer MEMS, right, in smartphone and iPad, tablet PC, and then we have in the near future we also have IoT device. IoT, Amazon Alexa is one of IoT device. You have a MEMS microphone array with wireless communication, and the voice connect into the cloud server with AI. Then they can try to provide a lot more application, right? So that I don't know if you have ever played with this kind of Amazon Alexa. You can find there's a lot more app, right? Smartphone has so many apps. Actually, your this kind of IoT smart loudspeaker also have a lot more apps, so that you can use this one to ask this kind of Alexa to do many things. You can smart home application. You control air conditioning, control lighting, and even can call this kind of Uber. So there's many different applications. So that this is a very common thing, right? Okay, and of course, in the near, I also have the project for smart building. More than 2 years ago, I worked with my friend, Professor Niff at MIT in ME department. So that we developed this kind of a CMOS MEMS sensor, particular thermal flow sensor integrated with temperature, humidity sensor. In this case, we want to think about how use multi-sensor for what? To energy monitoring and thermal comfort monitoring. How can with multi-sensors look at the important thing for the building, smart building, smart HVAC system, with actuator, smart window, with personalization, with also AI. So this become quite important. Why? For especially in Hong Kong, we have so many buildings, so that how can you use additional this kind of low cost sensor? Why? For this kind of smart building is a very important thing. So that I don't know if you have any idea about how much UST spend to pay the utility costs like air conditioning, HVAC, and also electricity every year. Huh? Do you have any idea how much UST pay for this kind of utility cost, utility bill, including HVAC and this utility electricity bill every year? 50,000 Hong Kong dollar. No way. Huh? Actually, I work with, because I got this big project, 10 million Hong Kong dollar project. I work with UST FMO. So that now I understand. UST spend almost 50 million Hong Kong dollar. 50 million Hong Kong dollar. For HVAC electricity. Can you believe? If we can have a smart HVAC system and then to save energy, right? I think this is very important, right? For every building in Hong Kong. So that at this moment, my team already come with the prototype. We I think I can show now in our test room at UST, we can say at least almost 15 to 20% energy, 20% of energy saving. You can calculate how much we can reset the money. So if you have all the advanced low cost, it's a sensor for smart building, you can really save a lot of money. It's not small money. Okay, so this is, of course, to be able to design this kind of MEMS sensor and with additional smart actuator with a big team, right? So that is not easy, but at least we are making a progress. Okay, so that of course, if some of you want to go this particular area, so you're also to work as student helper or Europe, so you can try to contact me. At least I think this is very important for Hong Kong. Hong Kong have so many buildings. Think about if we can really save this kind of 10% energy, 20%, that is a huge amount of money for Hong Kong, this kind of thing. And also reduce what? Reduce this kind of CO2 emissions. So It's really first save the money, and the same thing, right? Save the planet, right? So because once there's so many CO2 emission, we really can cause a big problem for the global climate change, right? So that is a big problem. So this is, from my point of view, I think this is very important for Hong Kong. Okay, here now I talk about some basic idea about this kind of the sensor, right? So we talk about several common kind of pressure sensor. Again, I think 90% of you have smartphone, and I believe you also have this kind of pressure sensor in your smartphone. But they don't call the pressure sensor; they call barometer. Huh? If your iPhone, I believe Android also have this thing, right? So that here they can measure pressure, but it's a barometric pressure sensor. Okay, so that they actually use as what? Measure the height, altimeter, measure height. No, so that your smartphone have GPS and man's motion sensor. They look at X and Y for guidance and control, right, with Google Map. But if you go to building, so GPS your GPS cannot get signal. So that once you have pressure sensor in smartphone, it can really look at this Z direction of the coordinate system, right? So this kind of altitude become some quite important thing. So how the pressure sensor work in smartphone? The idea is actually from sound mechanics. So basically, we have this kind of thin diaphragm. If you have a pressure apply, it called deformation, right? And then how this is input pressure, and then how we did convert this kind of mechanical input into electric output. So there are two possible ways. One is what we call the capacity sensing. That means once you have additional two pair of electrodes, if you code deformation, you change the gap, right? And then in this case, we can change capacitance. So in this case, we can convert pressure into this kind of a change of a capacitance. And then in this case, we can do this kind of sensing, because the capacity sensing. So basically, this is a very simple idea. We can really try to make a simple pressure sensor. Here, basically, we have what? Input pressure, right? And then change this kind of gap for this kind of capacitor. And then this one change the capacitor delta C, capacitor. And then in this case, we can measure the output signal, right? The voltage output. So this is basic idea of this kind of pressure sensor. Of course, your smartphone, the pressure sensor, they don't tell you about voltage output. Actually, they can directly do the calibration so that they give you this kind of the pressure and also this kind of height. Okay, so that's the pressure part. Okay, and then of course we have a second possible way is piezo resistance sensing. Again, idea is simple. Basically, you have a flexible diaphragm, and then if you apply the pressure, they change deformation, right? And then if you can have we call the piezo resistor. Here, you can make the micro piezo resistor, right? Once you apply pressure, and then locally they change the kind of deformation, and then this pressure will change resistance of this piezo resistor. So that in this case, we can also try to do this thing. And basically, for this particular way, with the pressure input, and then change the what? Change this kind of resistance of this piezo resistor, and then in this case, I have changed our output voltage of sensor. Output voltage. So this is a basic idea. We can really make a micro pressure sensor. Okay, so that of course in your smartphones, the main pressure sensor is not that simple. Actually, you have not only this is a pure mechanical way to describe pressure sensor, right? In reality, for this kind of real man's sensor, usually you have not only this kind of flexible diaphragm here, but also on-chip electronics to what? To amplify the signal and then do some maybe digital signal processing, so that this become very important, right? So that basically silicon pressure sensor exists in the market for more than 30 years, And then, so that we have not only 100 million, maybe 1 billion of sensor. Now, first sensor also used for smartphone, okay? And not only for a first sensor in the car, and also disposable first sensor in hospital, also smartphone, consumer electronic device become very big business. Okay. Here I show you another important thing, micro accelerometer. Okay, also in your smartphone. Okay, basically, micro accelerometer is a sensor or meter to measure this kind of acceleration. All right, if you have learned the basic physics or mechanics, engineering mechanics, so that basically, so we make it this kind of micro mass spring system. Here we have a micro mass and micro spring, so that this is a micro mass spring system. If you have input the acceleration, and then you will try to cause this kind of a deformation of this kind of mass spring system, and then so once you can input its acceleration and encode deformation of spring, and then what happens if you can have again input motion and then cause displacement of spring, micro spring, and then if you can make micro electrodes, and then in this case it changes the gap of capacitor, right? In this case, you can also convert input acceleration, and then output will be what? So basically, it's input acceleration, A acceleration, and then into the gap, change the gap of the capacitor. And then in this case, you can really, and then you try to turn into this kind of voltage output. So this is the basic idea how we can make this kind of MEMS accelerometer for your smartphone. Okay, so that again, similar to this burst sensor, the real MEMS accelerometer is much more complicated to solve some practical engineering issues. Here I show you some practical design. So basically, you still have micro. This is mass. This is spring. It's a folded spring, and then you also have a capacitor. Okay, capacitor is not only one; it's a pair of capacitor. Okay, so that here again you have an input A, and then cause deformation of the spring, and cause deformation, and then you change this kind of a gap of capacitor, right? So in this case, you can if you change capacitor into electrical output voltage, and then you really can make this accelerometer, okay? And then if you do calibration, then you can really try to measure this kind of acceleration, right? So that again, let me show you your this kind of smartphone app, so that you can, let me show you here. So you can download this kind of free app, and so that they can show you this kind of real acceleration as output, acceleration in X, Y, and Z direction. Okay, also show you about gyroscope sensor, and give you this kind of angular velocity. Okay, so that is now almost exists in every smartphone. Okay, yeah. Anyway, so here I just give you some basic idea about this. In reality, actually, we not only have a micro mass spring system, we also need to integrate the electronics, the IC. We could enter IC for what? To amplify signal and do signal processing, so that your smartphone accelerometer, you really have a micro mass spring system with ultra electronics. This is become so important thing now. So starting from 1993, analog device maker first service micro machine the accelerometer with signal conditions circuit, and then we have more and more 2 channels of accelerometer, and then your smartphone has 3 channels, right? 3 channel, this kind of acceleration. That's why you can see this is basically you have give you output, right, in X, Y, and Z direction. Okay. And how small is this MEMS accelerometer? This is the ADX202 MEMS accelerometer. your mass is about 0.7 microgram. Well, I think about human body weight, at least maybe 50 kilogram to until 70 kilogram. So this kind of a micro machine is 0.7 microgram. And for the size of this kind of, the fission size is about 1 micrometer. And the gap between this kind of micro spring and this kind of is about 1.2 micron. And then, so once you input 2G oscillation and the deformation of this deflection of this micro spring is about 5 nanometer. So this is really very, very small, right? Compared to a typical machine you see in your daily life, okay? And then, of course, we'll show you iPhone 3 is one of the important milestone for our MEMS community. So that after iPhone 3 uses kind of a 3-axis ST microelectronics MEMS accelerometer, and then all the other smartphone maker will really integrate MEMS accelerometer in every smartphone. And then, of course, iPhone 4 also use micro gyroscope. So what is gyroscope? Gyroscope basically is a sensor to measure input angular motion, right? So that here again, if you try to look at here, so that they can show you, we can measure this kind of angular velocity, right, in 3 directions, okay? So that how does it work? Basically, is micro gyroscope is a micro mass spring system. So that here I show you typical vibrating tuning fork. Is a continuous vibration, linear vibration. Once your angular motion, and then based on our engineering dynamics, so in the action of linear and angular motion, we have a Coriolis effect. Coriolis effect will cause what? It's an effective force to cause some deformation of micro spring. So in this case, if you have a good design, input is angular velocity omega, and output is the mechanical deformation spring. And then if you open your microelectrode, then in this case, what? You can change the gap of a capacitor, right? In this case, we can also make this kind of micro gyroscope. That means this case, you have input what? Angular velocity, we call omega, and then change what? Change the capacitor, the gap of a capacitor, and then we generate the voltage output. So this is the way. So now we can make the micro gyroscope. It's called a vibration-based micro gyroscope. Of course, compared with a traditional gyroscope in airplane, at this moment, I would say 99.9% of the gyroscope in airplane or aerospace engineering is still using the laser ring gyroscope because it's very mature. And gradually, I think in our MEMS community, gradually people want to make a more and more reliable, low-cost MEMS gyroscope or MEMS IMU for self-driving car or for aerospace engineering. But I think it still takes time because reliability is one of the important things for aerospace engineering. Okay. So then next one we show you is about. This is iPhone's 3. If you open up this iPhone 3, it's a PCB board, and then so this is a little chip. Again, it's not IC. It's a ST microelectronics 3-axis accelerometer, and then so that it's become, I think, quite important for every smartphone. And of course, iPhone or many smartphone has also the micro-magnetic sensor, or what they call the magnetometer. So again, if you open up your smartphone, and then I believe you can see this kind of magnetic sensor, right? And then so that they call the compass. So this is a 3-axis micro-magnetic sensor. So here I show you this particular one. Basically is a Hall sensor. Hall sensor is one type of magnetic sensor, and so that at this moment, I think the dominant MEMS magnetic sensor in a smartphone is made by a Japanese company called Hkust, AKM. I think occupy about 90% of the market for smartphone. Well, again, it's $1 billion business. Okay, so that of course another important area is about this kind of TI's digital micromirror. Why? It's a digital micromirror array, so that TI start this research of the DMD in 1977. After almost 20 years, finally, they can really make a real product. It takes a long time because this really not only the integration of about 1 million of micromirror, but also the on-chip electronics to control about million of this kind of micromirror. Look here, this is ends leg on this DMD micromirror array, right? So the typical one side of micromirror is about 30 micron. Okay, again, you about 1 million of this micromirror, and here, this kind of MEMS sensor mostly is not only important for smartphone, also for many this kind of product now. For example, Segway scooter use 5 MEMS gyroscope, right? Because 2 wheel actually intrinsically not stable. So in this case, we need to use this kind of sensor, micro gyroscope, stabilize this kind of the motion of this control, this kind of a 2 wheel transportation system. And here I show you this kind of how the DMD work. Basically, the idea is simple. So again, you have a micro mass spring system. You have a micro mirror and a torsional spring. So that and you have 2 pairs of microelectrode. And then if you apply the voltage on one of the microelectrode, and then you have what? Electrostatic force. And this force will try to apply as torque to rotate this micromirror on one side. If you apply the voltage on the other pair of microelectrode, then what happens? You turn this force will turn this mirror in another way. So in this case, we can digitally to rotate micromirror. Okay, so that is the way people make this kind of micromirror. Okay, and so of course, in reality, in order to make this kind of control, 1 million of micromirror is not easy at all, because you cannot use 1 million wire to control this kind of your micromirror chip. So in this case, you need to have integrate CMOS this kind of switch to control this kind of operation of this kind of micromirror. In this way, you see, you rotate this angle plus minus 10 degrees. Okay, and this one has been used for computer projector or even pico projector. I remember Sensor also tried to make this kind of a smartphone with this kind of pico projectors. Okay, Sensor also make the DOP for TV, and people also found DOP chip can also 3D like TV or 3D like a projection is also quite useful. Right? And another important thing is about inkjet. Inkjet is another important kind of MEMS devices. It's an actuator. Basically, it's based on heat transfer. So once you have micro heater, and then you have micro nozzle or roller face. So if you have ink here, right? So if you provide energy to the micro heater, and then to heat up your ink from room temperature to I think about 200, 300 degrees C, and then you will it's a boil water in micro scale, and then liquid will turn into vapor bubble, and then suddenly this vapor bubble will change density a lot. Why? The density of liquid and vapor it differ by almost 1,000 times. So in this case, this have high pressure. This high pressure will push ink out of a nozzle. Originally, you have continuous jet, and then you break into the droplet. So this is the basic idea how we can do this kind of thing. Well, of course, in real product for inkjet printer have, so you have not only one inkjet unit, you have at least array of inkjet units. So you have an electronics switch to do control of this inkjet unit. So that here I show you the basic idea. Basically, you have resist heating in micro heater, and the heating rate is like 1 second you can heat up to 1,000 degrees C. What do you think? Do you think the inkjet will hit at 1 million degrees C? Huh? Probably it's not, right? If 1,000 degrees C, I think you'll melt. So that of course, the inkjet actually you heat up. No, the ink for about 10 or 20 microseconds, so that your temperature go from room temperature to about I would say 100, 200, or 300 degrees C only, right? Not 1 million degrees C. And again, this kind of thing will be the bubble used as a pump to push liquid out of this kind of nozzle. And then because this kind of pure mechanical issue, hydrodynamic instability, so that the competition of the inertial force like Newton's law and surface tension. So this kind of conditioned jet will break into the droplet, and then you can do the kind of printing. And typical here, this show you the old HP inkjet. So it's about micro nozzle, right? Each size, I would say about 100 micron. And in this inkjet chip, you have a 15 nozzle, okay? But nowadays, you have a much more advanced this kind of inkjet now, because we want to have what? High speed, high quality printing. So in the case, all the inkjet you are using now, you have about, I would say, more than 6,000 of this micro nozzle. And then you have to have integrated microelectronics to control about this thing, right? So this rich, high speed, high quality printing, okay, is also required this kind of micro machining. And then of course, we'll find this kind of thing. This X is price and Y is number of nozzle. So that in old day, 20, 30 years ago, we have a 50 nozzle, but nowadays we have 6,000, more than 6,000 of nozzle in the commercial, this kind of inkjet. So that's become very important. Yeah. Of course, we also have more love for not only for this kind of IC. People find we do more love for DNA sequencing. Can you imagine? So that about 20 years ago, we had this kind of a tabletop machine do the DNA sequencing, and then people spend 2.7 giga, 10 to the power 9 US dollar to do human DNA sequencing. Spent 11 years, and then gradually, some people come with some new way, like a crack vendor, they have companies spend 100 million, 3 years can finish DNA sequencing. And then we have additional technology to 454 was spend 3 months, 1 million. We can do the DNA sequencing, and gradually we have additional company spend 2 weeks with $60,000, and then we have Illumina helical, and then do the 40,000 US dollar, and then nowadays, as I show you, Oxford Nanopore, it's portable, just like smartphone size DNA sequencing machine now. So this micro and nano machining is not only for IC main sensor, also important for biotech DNA sequencing. This is a very important thing. And in the near future, we'll see this kind of biochip or DNA sensing or sensing about bacteria will become very, very important. Okay. And here, let's quickly show you about fabrication. So how we can do microfabrication. In general, we have surface micromachining, also have a bulk micromachining. So surface micromachining basically is we try to start from our silicon wafer. We can do deposition and pattern a thin film material. Okay, and then so you start from silicon wafer, we deposit some thin film layer and sacrifice and do some etching and deposition, and then we can make additional layer, structure layer, and then we try to sacrifice, remove sacrifice layer, become freestanding micro beam, right? So this is called surface micromachining. Another thing, we have a bulk micromachining, where wet etching with wet chemical, KOH, EDP, and then we have what? We make an optical mask, and then we etch the bulk micro silicon, and then this is bulk micro machining, and it really depends on this kind of orientation of silicon wafer. Again, wafer is single crystal silicon wafer, so crystal orientation become very important. And then also we have used different kind of chemical as part of etching. So these are two important areas people do some micro machining for IC, for MEMS devices. So let's look at this physical scaling one. We look at the scaling micro machine. Basically, we look at all the force, Newton's law, all the forces involved in this operation of micro machine for your sensor, for actuator. We look at force in micro world. Basically, a length scale, scaling law in sound mechanics, fluid mechanics, heat transfer, and then so this is and look at some micro thermal physics and electrostatic. So basically, we look at based on our high school physics or our UG physics, right? We look at this kind of friction force between this kind of a big mass on the solid surface, right? Typically, we learn, right? Friction force proportional to the mu n in normal force, right? And then, but in micro scale, it turns out friction force is now actually it's very different from macro scale. Right? In macro scale, our friction force independent of a contact area. If you orientate it this way, this way, and the friction force is, but in micro scale, so actually the friction force depends on contact area. Okay, and another important thing is this kind of friction force may cause some problem, restrictive problem. If you do some micro machining, and if you have some additional surface tension force, this can cause some problem. So your micro structure may stick to the substrate of silicon wafer. Then it's really a big problem in the old day, like 20, 30 years ago. And people have to understand the basic microscience in order to make a working MEMS sensor actuator. Okay, and of course, surface tension is also a very important thing. Right? In micro machine, so that the surface tension become very important thing, right? So that you see the capillary effect. Over you have learned the basic this kind of physics behind, so that how we use this kind of surface tension for this micro machine. Here I show you an interesting idea. Surface tension driven microfluidic device basically is electrically require voltage, and you can change surface tension. In this case, I can try to manipulate this droplet. Okay, so here it makes it kind of simple, like wetting based micro pump. And this idea, this is not new actually. So when I was at UCLA more than 20 years ago, so Professor John Hoon Lee actually he tried to make this kind of micro motor, right, using surface tension, and then in this case become very useful thing, right? And of course, people think about how to use this kind of surface tension to make a practical device. For example, Ray Optics, it's a company in France. They try to use kind of electrowetting to control surface tension to make what zoom lens for mobile phone camera. And again, for surface tension become very important in its micro machining. Okay, so that if you go beyond millimeters, say, and then surface tension become much more important thing. Okay, again, in order to make some critical success about MEMS product, so important thing here is you need to have a market, right? At this moment, of course, smartphone is $1 billion business, and then how you can make a good MEMS sensor and replace existing very bulky device. So that's very important. And then you have a good idea design, a combination of mechanical engineering with electronics. Then you can design of a good MEMS sensor, right? Have low cost, high performance sensor. That is very important, right? At this moment, in order to make this kind of successful MEMS product, we overcome technology barrier. Typical thing is how we make this kind of micro machine sensor on top of electronics, or you want to think about electronics fabrication process on a micro machine. So the combination of both, sometimes you really have a problem, the internal fabrication process. So that at this moment still, is not easy. So of course, if you have at this moment the fabrication, design fabrication of MEMS sensor cannot be separate. So that if you have a 10 or 20 years experience, then you can really understand about how to work on design and fabrication of MEMS sensor. So that is very important thing. Another important thing, the packaging design. Compared with IC, the packaging is still very difficult. Every MEMS sensor need a different type of way to the packaging. Okay. Anyway, so that at this moment, many company, right, that can really make a real product. Most likely, it's a big company, major semiconductor company. They have a long-term money to spend to do R&D. They really make a good MEMS sensor. Right? If a small company, they really think about how to work on design, to work with semiconductor foundry to or MEMS foundry to really make a product. Okay, so in the near future, I would say we have a lot more MEMS device. Not only smartphone, wearable device, drone, automotive industry, robotics, and all the IoT, smart building, all in the near sensor. Okay, and of course, in the near future, these slides come from the lecture by Dr. Paul Huang, founder of Cadence and for Media, the company in Silicon Valley. So that he make the interesting talk. Okay, so that in the near future, 10, 20, or 30 years, integration of CMOS MEMS sensor with AI, we not only make an SoC, but edge on chip, so that your computer, smartphone will have a much more sensor with AI for all the future work. Okay, I think we run out of time, so that I don't know if you have any question. If question, you can try to send me through this kind of chat. Okay, do you any question? Any question? I think we run out of time, so that again, so that if you have question, maybe you can ask through this kind of Zoom chat or through the cameras, so that any other question? No question, then probably this is the end of the dead lectures. Okay, and then I think I will try to record this kind of a video and save on our cameras for you to share. For those of you cannot attend today's lecture, so that I think still you can try to watch this kind of video on our thing. Okay, I think probably that's it for today's lectures. Okay. Okay, I think bye-bye.